Welcome back, everybody. We are nearing the end of our chapter 10 chapter on momentum, and we're finishing up with elastic collisions. Elastic collisions, and these are collisions, as we mentioned before, and I've just briefly mentioned it in class, that have two things that are conserved. You probably recall from inelastic collisions that momentum is conserved, that the total initial momentum has to be equal to the total final momentum. And we took that when we broke that down into M1 V1 or MI VI equals M2 V2 or M final V final, and so forth. So we're familiar with that. But what is also true with elastic collisions is that energy is conserved. The total kinetic energy of the system beforehand is equal to the total kinetic energy of the system afterwards. And this is different because with inelastic collisions, we had energy loss. We had cars that were crumpling when they would crash, or we would have objects sticking to each other. Here we have objects transferring energy perfectly. Now, in the real world, at least in our macro world, our everyday world, there's no such thing as a perfect elastic collision. Two things hitting each other don't transfer kinetic energy absolutely perfectly, but we can get very close. It is, however, true that at the subatomic world, we can have perfectly elastic collisions. We're talking about subatomic particles. So it can happen. It's not just a theoretical thing. We just don't see it happen in front of our eyes on a daily basis. But we can get very close. And those Newton's cradles with those swinging ball bearings are good examples of elastic or very close to elastic collisions. So let's take a look at this slide right here. We have established that conservation of momentum has the total momentum beforehand being equal to the total momentum afterwards, final and initial, which, by the way, I want to clarify something here. I'll erase that and I'll write it again. These little symbols here are called primes. There's a couple different ways to write this. In this case, prime simply means final. Like, this is the initial momentum of an object, and this is the final combined momenta of these two objects. And the reason we only have one momentum and then equaling two momenta is because, we said, this is where we have one object striking a second object at rest, and then the two objects take off with different velocities. So this is really just the momentum of the first object. The second object, M2, is at rest, and therefore the momentum is 0, which is why there's no value for it right there. But don't be scared off by these primes. They simply mean final, okay, or the second version of it. That's really what prime means. Okay, so that's conservation of momentum. Yes, we know that. We also know conservation of energy, or conservation of kinetic energy, tells us that this is our initial kinetic energy, and if we only have one object moving and the second object is initially at rest, then we're only going to have one kinetic energy here. But once they strike each other, we're going to have K1 final and K2 final. But what is true is that they have to equal each other. This has to equal that. The kinetic energy going into a system must equal the kinetic energy coming out of the system if it is to be an elastic collision. Okay? So both of these are true, and both of these I think we've covered sufficiently in class that they can be understandable. Now here's where there's going to be a great big jump to these two equations right here. Where it says solving with very messy algebra, that is no joke. We really take the conservation of momentum equations and the conservation of energy equations, and we combine them algebraically, do a lot of substitution and operations with them. And I can show you if you want. In fact, I'll post it online. I've got 3 pages of going from these 2 equations here and here to these 2 equations here. But it does work. And here is one instance where I'm going to tell you, just take my word for it, this works. Okay, now these primes, once again, they mean final. In fact, I'll just write a little f here. V1 final and V2 final coming out of a collision. So we have, for this scenario, we have one object is moving. That's M1. So we might have a truck, okay, a big dump truck moving towards a car which is stationary, okay, not moving. Well, they're going to collide. There's going to be a collision, and both the truck, that's a very bad truck right there, the truck and the car, I'm pretty sure, are going to be moving afterwards, especially if that car is considerably smaller. They're both going to be moving. So these 2 equations, for this is object 1, this is object 2, it's initial, 1 final, and 2 final. These equations solve for the final velocity of each object. The masses don't change, but the velocities do. So let's apply this to a problem. We're going to have an elephant run into a fly. Okay, an elephant in motion running into a fly. And I think what I'll do for that one is I'm going to make a second video, so I'll just see you on that one. So I'll see you in just a few minutes.